All right, so today we're going to talk about theorems and how to prove them, and then we'll introduce three new equivalences. Transposition and material implication are in the book, but negation conditional is not in the book, and it's really worth learning, so we'll talk a little bit about that one as well. So in a previous lecture, I said that we are expressing our equivalences as theorems. So, for example, our simplest equivalence, which is double negation, which tells us that A, if and only if, not A. We express like this with the turnstile on the left-hand side, and nothing over here, right? No propositions over here. And so what this is literally telling us is that A, if and only if not A, can be derived. It literally follows from zero other propositions. Now, that sounds paradoxical. We're always told that you can't get something from nothing, but it actually turns out to be a perfectly intelligible idea, and it's just true that we can get something from nothing in logic. So how does that work? Well, in chapter 3, you'll remember that we introduced the idea of a tautology, which is a necessary truth, or a proposition that is true under all possible interpretations in its truth table. So whenever we talk about the truth and falsity and also the interpretation of propositions, what we're talking about, what we're dealing with, is an area we call semantics. That's just the name of the area of logic that addresses these concepts. And in this chapter 4 on the propositional calculus, we haven't been dealing with semantics at all. We've been developing the idea of proof or derivation and developing a system, the propositional calculus, for doing proofs. So it's interesting that actually you never need to talk about semantics when you're talking about proofs or proof theory. In logic, they're totally separate subjects. So even though they're distinct concepts, it turns out that anything we call a tautology in propositional logic is going to be a theorem in the propositional calculus. So if you think about this intuitively, you'd say that, look, if a statement is true under any interpretation, if it's a necessary truth, if it's a tautology, then you'd think we should be able to assert it, anytime we like, without giving reasons in support of it. And that's really just the layperson's way of saying that every tautology should be a theorem, and vice versa. And we preserve that basic intuition. So not all theorems are equivalences. We introduced the idea of a theorem when we talked about equivalences. Actually, the book introduced it a little earlier. But there's lots of things that are theorems that aren't equivalences. So if P, then P is a theorem. It follows from no premises, and so is P or not P. It's called the law of the excluded middle. So neither of these have biconditionals in them, so they're not telling us that one formula is equivalent to another. So we write these like this, right? If P, then P, and P or not P follow from no premises. So these expressions literally say that. Now, how do you prove these things? Well, it's actually really simple. Anytime you prove a theorem, you'll have to use either negation, introduction, or conditional introduction. So you're actually going to start out, the very first line in the proof is going to be a hypothesis, which you ultimately discharge, right? So voila, you get a proof without any assumptions. So that's the trick. All right, so let's go ahead and prove those little theorems. Let's prove if P, then P. How's that going to work? Well, that's conditional. So we're going to proceed here by conditional introduction, right? So hypothesize P, and now what do we want? Now notice we've indented here. It's kind of hard to see that. We've indented. Can't see it because it's hard to see because there's nothing above it to compare it to. But we have done it. So P, and so what do we want? Well, we want P. Well, but we have P, right? Our old trick. So we can now assert if P then P by 1 through 1 conditional introduction and drop a teeny weeny line, right? So what is this telling us? It's telling us that if P then P follows from no assumptions. How do you know that? Well, there's no assumptions. There's a hypothesis, but that's not an assumption, and it was discharged. Almost as easy, P or not P. Here we'll proceed by negation introduction. You can do this on your own, I'm sure. Just go ahead and shut it down and produce it. So we'll hypothesize, again, an indent. It's not the case that P or not P. And then just apply De Morgan's to that. So not P and not P by 1 in De Morgan's. And this is kind of cool. You now have a contradiction. Not P and not P are contradictory formulas. And that's what you wanted, was a contradiction. So here's one of these funny times when you can get the contradiction without having had to do an and introduction. So now you can just go ahead and assert the negation of the hypothesis. It's not the case that not P or not P. And go ahead and drop your line. Now, of course, you didn't want, it's not the case that not P or not P. What you wanted was P or not P, but you can have that with 3 and negation elimination. Or double negation too. Okay, so that's how theorems work. So it's also interesting to note here that any valid argument can actually be stated as a theorem. So if you think about something like our rule of conditional elimination, which we state as a valid argument like this, that's based on 2 premises, right? If P, or excuse me, P and if P then Q. We can actually state that as an argument with 1 premise if we substitute the an and, right, for the comma. So now it says P and if P then Q yields Q, right? So how can we convert that into a theorem, which is to say a sentence or a formula or proposition that follows from 0 assumptions? Well, the answer is that we just take this whole thing now, which is just 1 proposition, and we push it all the way over, right? And we introduce a conditional, right, which substitutes for the turnstile right here, and then we move the turnstile to the front. So if we put the turnstile in the front, move this all over on the other side, it says if P and if P then Q. And then we can prove this is a theorem. Proving it as a theorem is really no different than proving that this is a valid argument. It's just that you're going to use hypothetical rules to do it. Okay, well, let's introduce some new equivalences now. We'll start with transposition. Transposition is called transposition because you're transposing, which is you're switching the order of the conditional. So if you go in the forward direction, if you have if A then B, you turn it around and you got B in the front and A in the back, but now it says not B then not A. So if A then B, if and only if not B then not A. And of course it goes in both directions. Now this is actually a really straightforward thing to prove using using modus tollens, and I think you could probably do this on your own, so why don't you give it a try. So the thing to be aware of is just what we were talking about previously, is that you're proving a theorem, right? And you're proving a biconditional, which means that you're going to hypothesize. The typical way of doing this is you're going to hypothesize if A, then B, and derive if not B, then not A. And then after you're done with that, you'll hypothesize if not B, then not A, and derive if A, then B. And once you've done that, you'll just put them together with a biconditional introduction. Okay, so hopefully you've done that. Why don't we check your work here? So we hypothesize if P, then Q. And then the next move would be to see that you're trying to derive a conditional. And whenever you're trying to derive a conditional, you want to typically you want to hypothesize the antecedent again. So you got not Q, which of course gives you not P by modus tollens, which gives you your first. You get to jettison your second or discharge your second hypothesis now. So you got if not Q, then not P, and which of course allows you to assert if P, then Q, then if not Q, then not P. So that's your first conditional. And then you just go the other way, right? Hypothesize if not Q, then not P. Works exactly the same with modus tollens, except you've got a couple of double negation moves in there. So you're allowed to now assert if P, then Q, drop a line, and now you're allowed to assert the full conditional, drop another line. So now you have both conditionals, put them together, and you've got your theorem. Okay, so that's just the proof of transposition. We didn't use it. So how do you use transposition? All right, so if you did this yourself, you probably proceeded by conditional introduction, hypothesizing S, and that's great. You should never feel like you've done anything wrong by proceeding in that way, and it'll always work. There's just times when you don't really need to, and this is one of these times. So we'll proceed without it. So if you look at 1 and 2, you'll see an interesting relationship here. We have the antecedent of 1 being the consequent of 2. And so with hypothetical syllogism, you would be able, if you wanted to, assert if P, then not S. Well, why would you do that? Well, if P, then not S looks suspiciously like the transposition of if S, then not P, right? So let's try that out. Let's go ahead and write if P, then not S by hypothetical syllogism. And let's go ahead and apply transposition to line 3. Now, how do you do that? Well, you got to be careful. Just go ahead and if you write the rule of transposition, right, it's that if you have if A, then B, that's logically equivalent to, right, if not B, then not A. Okay? So if you're going to substitute for this formula, if you want to substitute this for this, then you're going to have 2 negated subformulas, right? But you don't have 2 negated subformulas. You have if P, then not S. So a non-negated and a negated. So that means you're going to have to treat if P, then not S as if A, then B. Okay? Now, if you treat P as A, right, and not S as B, then when you essentially flip them, right, you're going to get not S, then not P, right? So that's what you got to write. So just be careful, do your bookkeeping. And the other thing you could have done is you could have applied double negation to not P and then flipped them as a result of that and gone the other direction. But so we've got if not, not S, then not P, and so now we'll apply our double negation now. And we've got if S, then not P, which is what we wanted. So that's how transposition works. Very simple, straightforward equivalence. Okay, let's talk about negation conditional, which I said earlier is not in the book, but is also very useful. And part of the reason I like to introduce it is because it is in the book in the sense, in theory or intuitively, because it'll remind you of the refutation tree rule. So the negation conditional says that that it's not the case that if A then B is logically equivalent to A and not B. So the refutation tree rule, you'll recall, allowed us to write it's not the case that if A then B to A and not B, right? But it didn't allow us to go in the other direction. So here we can do that as well. If you have A and not B, you can substitute it's not the case that if A then B. Now this is actually a very interesting proof to do, and you should do it. And we'll go ahead and go through it now. Now if you're a little tired and you want to just say, oh, I'll just give me the equivalence and show me how to use it, that's okay, but it's really good practice to do the proof. So that's what we're going to do right now, and you should go ahead and try to do that, or if you want to just skip to the next slide where we actually put it to use, that's fine, but then when you have a little more energy, come back and try to prove it. Okay, so we're going to go ahead and prove this, especially because the book doesn't give it to us. So how are we going to proceed? Well, again, we're proving a theorem, which is a biconditional, and so we know how to prove biconditionals now. So let's go ahead and start by hypothesizing it's not the case that if P then Q. Okay, so what we want to demonstrate is P and not Q. So now what we want to derive is P and not Q, and that's a conjunction, not a conditional. So it looks like we're going to have to hypothesize again by negation, and for a negation introduction, it's not the case that P and not Q. And now, of course, what we want to do is generate a contradiction. Well, and obviously to do here is apply De Morgan's, right? Equivalence we learned last time to get not P or not Q, right? The negation gets distributed and we switch it to a disjunction. So that's nice. That was a fun thing to do. So now we have not P or not Q, but it doesn't really look like we're any closer to producing a contradiction. This is a disjunction, of course, so we can't just break these apart. So what are we going to do? And the answer is that we're just going to stare at it, and we just have to start playing a game of what if, right? Because just remember, you're trying to produce a contradiction, and so what can you contradict here? You could conceivably you could come up with a way of contradicting one, or contradicting two, the negation introduction hypothesis itself. But since you can't do anything to one right now, there's no way you're going to do that. So it looks like our only hope would be to try to figure out a way to contradict one. And so how would you contradict one? Well, you would contradict one by demonstrating if P then Q, right? By showing. I'm not saying it's obvious that you can do this, but by showing if P then Q, because that would contradict If not P, then it's not the case that if P then Q. So how would you show if P then Q? Well, you would hypothesize P for a conditional introduction. And remember, you're just trying stuff here. It's not clear that you can do this, but maybe now, having gone this far, you can see that it's clear that we can do this. So go ahead and stop and see if you can actually show if P then Q. Go ahead, and I just wrote all that out as far as the strategy is concerned to emphasize that you are doing some creative hypothesizing. Let me just erase the strategy so you can see that more clearly now. All right. So how do we get if P then Q? Well, we create not P through for and double negation, and by disjunctive syllogism on 3 and 5, we get not Q, which of course is Q, which allows us to assert if P then Q. And so now, right, we discharge that hypothesis. Now we've actually, amazingly, created a contradiction between 1 and 8. So we have to assert the contradiction by 1, 8, and introduction. And so now we're allowed to assert the negation of our hypothesis. It's not the case that not P and not Q by 2 through 9 in negation introduction. And as a result, we drop a line, and as a result, we have P and not Q by double negation, which allows us to assert the conditional that we wanted. Okay? So that's a real logjam. That was something that we just had to noodle about and figure out, and it's very different in the sense that you really had to get creative to figure that out. But once having done it, it's pretty cool to see that something that looked impossible is actually quite possible. Now, this is just one way. The other way is actually quite a bit simpler, and it's something I would expect you to be able to do on your own. So you're going to hypothesize P and not Q. Of course, we are now going to try to demonstrate if it's not the case that if P then Q. And so it makes sense. So this is a negated conditional, not a conditional. So it makes sense to go ahead and hypothesize for negation introduction, if P then Q. It also actually would have made sense to just go ahead and do an and elimination on P and not Q beforehand if you wanted to. That might conceivably save some work by making P and not Q free and clear. But I didn't. I took a chance. So I'm going to go ahead and create P by 13 and elimination. That's going to, and not Q by 13 and elimination here, which, as I said, you could have done earlier. And that's going to give me Q by 14 and 15, conditional elimination, a very straightforward move. What are we trying to do? We're trying to get a contradiction, but now we have a contradiction with Q and not Q, which we can state, 16 and 17, and introduction. And having achieved our contradiction, we can assert the negation of our hypothesis. So it's not the case that if P then Q, drop that line, right? And now, of course, we've got our conditional, okay? So now we're not done completely, but we're very close because we now have 12 and 20. So now we assert the biconditional, and we have proved our rule. All right, so how do we use negation introduction? Well, here's a proof where you can go ahead and use negation introduction. Why don't you give that a try? Okay, so here you're trying to prove a disjunction, which you know, I mean, if you could do it, you could just prove the prove one of the disjuncts, if that were possible, to prove just one of the disjuncts and add on the other one, either the first or the second. But you've got a negated conditional, right? And we just learned the rule of negated conditional. So what if we just go ahead and applied it, right? So we got P, and it's not the case that R and S by 1 and negated conditional. And the nice thing about that is that we now have a conjunction which, we can go ahead and just break apart. So we have P, and it's not the case that R and S. And now, right, again, just to sort of break things down, you've got a negated conjunction, and negated conjunction, if you apply the De Morgan's equivalence, gives you not R or not S. So now you have this disjunction, and you have P, right, to work with to try to demonstrate P and not R or P and not S. Okay, so these two are conjunctions, right? So it looks like you're going to have to, is there any way, if you look at this, is there any way to just get P and not R or P and not S? The answer is no. I mean, there isn't any way to do that, because this is a disjunction. You can't just take this apart. So it looks like we're in the realm of a disjunction elimination proof, right? So in a disjunction elimination proof, what you're going to do is hypothesize one of the disjuncts, get your conclusion, and then hypothesize the other disjunct and get your conclusion. So why don't we hypothesize for conditional introduction, not R, right? And now what we want to demonstrate, having hypothesized not R, is we want to demonstrate this whole thing, P and not R or P and not S, right? We want to get the whole conclusion twice. So we can do that now, though, right? We've got P and we've got not R, so we can actually assert P and not R, and then just add in P and not S by or introduction, right? So that gives us, if not R, then P and not R or P and not S by 6 through 8 conditional introduction. And I bet you can see we're just going to do this again with not S. So you know how to do that. Go ahead and give it a try if you haven't gotten this far on your own. Hypothesize not S, right? Now you have P and not S by 3, 10, and introduction. So now you can just add in P and not R on the other side by, again, on or 11 or introduction. If not S, then P and not R or P and not S, same way. And so you got both your conditionals. So now you can go ahead and assert using disjunction elimination by 5, 9, and 13 the conclusion you were after. So that's kind of a long proof just to demonstrate the value of negation conditional, which we got out of the first step. But again, a very good exercise. Okay, the last equivalence is material implication, which is in the book. And something that you'll also recognize from refutation tree rules, right? At least in the forward direction, you'll remember that whenever we had if A, then B, we would write not A or B, right? Remember that? Well, that's what this says going this way, but it also tells us that it's an equivalence, so we can go the other way as well. So if you have not A or B, you can assert if A, then B. All right, so this has been a long lecture, so we'll skip the proof of this. It's actually not a difficult proof either, and you can definitely do this one on your own. Okay, so here's a proof of a theorem. It's not the case that M and B, or M if and only if B. Now, if you were to do this on your own, which of course I encourage you to do, you might say, okay, look, I mean, this is not a conditional, so I'm just going to go ahead and proceed by negation introduction and just negate the whole thing. And actually, that would work. It's a good way to do it, because if you negate this whole thing, you're going to be able to apply De Morgan's. That'll turn this into a conjunction. You're going to get a wealth of information, and you'll be able to prove it. You'll be able to prove it that way. But another way to think about this, and this comes in handy down the road, is to say, okay, look, this is a disjunction, and I know that every disjunction is actually a conditional by material implication, right? So think of it this way. Think of M and B as A. And so we've got not A or B, right? So remember, not A or B is, by material implication, logically equivalent to if A, then B, right? That's the rule we just learned. So if A, then B is logically equivalent to not A or B, and that's not A or B. So if you demonstrated if A, then B, in other words, if you demonstrated if M and B, then M if and only if B, you'd be able to convert it to this in just one step. So let's try it that way, see how it works out. So let's hypothesize M and B and try to get M if and only if B. Now it turns out that's pretty easy. We are going to, I just restated our strategy there. We're going to get M and we're going to get B by 1 and elimination. That looks like it's been indented a little bit. I didn't mean to do that. So we have M and B, and now we're going to prove M if and only if B. So we'll hypothesize M, reiterate B, and we've got if M then B. Then we'll hypothesize B. Kind of odd to be hypothesizing something you already have, but we're trying to get the conditional. So hypothesize B, reiterate M, and so we have if B then M, and so now we have our biconditional M if and only if B, and so now we can actually write our whole conditional M and B, then M if and only if B. And that's what we wanted, but we're not done, but that's what we wanted, because now with material implication, we can just convert that over. Not M and B or M if and only if B by 11 and material implication. Now material implication works in all sorts of ways that are useful, but this is one that allows us to expand the range of proofs that we can apply conditional introduction to. Okay, so let's go ahead and finish up by just reviewing our new equivalences and how to prove theorems.